All right, the next concept in this video is going to be, in this unit on moles, is going to be a concept called hydrated compounds. A hydrated compound is an ionic compound that, when it crystallizes in a solution, water molecules get bound up in the structure. So here you can see a molecule in which copper sulfate, the ionic compound, has literally bonded to 5 other water molecules, creating the crystal. And that just continually stacks on as we add more and more copper sulfates. So the chemical formula of this compound would be copper sulfate dot 5H2O. Now when this crystal forms, this solid forms, it's not like feeling a sponge. You're not going to feel moisture at all. It still feels like a rock-hard ionic crystal, but inside that crystal network, there's a bunch of water molecules attached. And for every 1 copper sulfate, there are 5 water molecules attached to it. Okay? Now, this is what a hydrated compound looks like. Now, with a hydrated compound, if I heat this hydrated compound, if I heat it, the energy from the Bunsen burner or whatever I'm using to heat the material has enough energy that it can come by here and it can sever these attractive bonds that the water has to the copper sulfate. And when these sever, the water leaves as steam, leaving behind the ionic compound, which still has a very high melting point. So the products, when we heat hydrated compounds, is copper sulfate solid, and we have removed the 5 water molecules. So literally, the dot means that the water is chemically bound to the compound. Heating it will separate it into the ionic salt and the water that now leaves as steam. So when we heat the crucible, heat the substance, the material ends up going down in mass. Its mass reduces because moisture is being eliminated from the crystal. What's left behind is the substance that does not have water attached to it, and the salt that has no longer water attached to it is said to be anhydrous. Anhydrous means without water. So the salt that is fully dried is called the anhydrous. The salt that contains the water is called the hydrated compound. So just some vocabulary for you to understand about hydrated compounds. So in your packet on page 13, you have this sheet, and actually in this year I forgot to include the hydrate, so I gave it as a separate packet that you can find in Canvas. So these hydrated compounds, there's a couple things you have to be able to do. First of all is you have to be able to name them. To name a hydrate, we literally name the salt, and the salt is held together by ionic bonds. So we're going to use ionic bonding rules. And then, based on the number of water molecules that is attached to it, we use the word hydrate to mean that water is attached to it, and we slap on a prefix to indicate the number of water molecules that is attached to the ionic compound. For example, if I look at the one that we were just doing, the CuSO4.5H2O, the CO is copper. And when we look up copper on the Chem Helper, you'll notice that copper can be +1 or it can be +2. Sulfate has got the ionic charge of -2. So that can tell me, by using ionic rules, that it has to be +2 to balance the -2. So this is called copper 2, which is the charge on the sulfur, charge on the copper, excuse me. This is copper 2 sulfate. And since there's 5 water molecules, the prefix 5 is penta, we would say copper 2 sulfate pentahydrate. Okay? The one right above it, NH4, is called ammonium. It's the ammonium ion. C2O4 is the ion called oxalate. I know very few of you would probably know that. That's okay. So it's ammonium oxalate, and there's now only 1 water attached. The prefix for 1 is mono, so we say monohydrate. Okay, I'm going to pause the lecture now. If you, on a sheet of paper, would like to go ahead and do the name for the last compound and then write the formulas for the last 3, When you restart the lecture, the answers will be provided and you can check to see if you've done it correctly. I'm going to pause the lecture now. All right, so the answers you can see here, the next one is barium hydroxide. Barium does not need Roman numerals because it's in the S block. Barium hydroxide at 8 waters would be octahydrate. Sodium acetate. Sodium has got a +1 charge, and acetate, which is that long C2H3O2 ion, it's got a -1 charge. Therefore, they bond in a 1-to-1 ratio, so we get the formula NaC2H3O2. And trihydrate tells me that there's 3 waters, so I put dot 3H2O. Cobalt-2 chloride. Cobalt-2 tells me the charge on the cobalt is +2. Chloride is -1. Cross-dropping, we get the formula COCl2. And hexahydrate means there's 6 water molecules. Calcium chloride is also, calcium is +2, chloride is -1. So again, we cross-drop and we get 1 calcium for 2 chlorines. And we get CaCl2. Dihydrate means we have 2 water molecules. So that's how we name hydrated compounds. Name the ionic compound and the number of water molecules to add a third word to the name. The last concept here now is how we can use this dehydration process to be able to be able to figure out the chemical formula. So in the lab, one of the labs that we've done in previous years is where I give a hydrated compound and I tell students that their job is to figure out the number of water molecules that is attached to the ionic salt. And the technique we use to do that is we heat it. And when we heat it, the solid that is left behind is the anhydrous salt. The water is in a gaseous state and it is left to escape. So when we heat this thing, we're going to see a mass decrease, which allows us to figure out the mass of the water that was present in the crystal. By doing some math, we can then figure out what the amount of water, or in this case, what the value of X is in this problem. Okay? So here we have a barium chloride unknown hydrate. Our goal here is to figure out the number of water molecules that is attached. We're going to heat it, and what we're going to be left with is the solid barium chloride. And what is separated is a certain number of water molecules that leaves as a gas. We can see in the mathematical problem when we read it, it says we're going to start out with 5 grams of the hydrate compound, which is the initial substance. Again, this entire thing is called the hydrated compound. When we heat it, what is left behind is 4.26 grams. We can see that the mass has dropped, and that is because water or moisture has left the crystal. If I subtract these two numbers, this will tell me the mass loss, which is also equal to the mass of the water that must have been in the crystal. So step 1 is to figure out the amount of water that was present in the compound. So now we know that there was 0.74 grams of water in the compound and there was 4.26 grams of anhydrous salt present. The two numbers that we write should effectively add up to the initial mass of the compound that we started with, which it does. So step 2 is to write down the masses of the water and the mass of the salt present in the compound. Step 3 is to convert each of the gram quantities into moles. We literally are treating a hydrate problem like an empirical formula problem. We are doing the same exact mathematical work, but instead of figuring out the grams of one element to another, we're figuring out the grams of water to the grams of the salt. So to convert grams to moles, we have to know the molar mass of the chemical compounds. So I'm going to add up 2 hydrogens and an oxygen, and we get 18.02 grams. That is the molar mass of water. We are then going to do the same thing for the barium chloride, which barium is got an atomic weight of 137.33 plus 2 chlorines, 35.45 for each. and we get a mass of 208.23 grams. Okay, we'll go ahead and divide 0.74 divided by 18.02, and we get 0.0411 moles of water. And dividing the other one, we get 0.0205 moles of barium chloride. Last step, just like in empirical formulas, we identify the smallest number, mole quantity, and we now divide each of these by that number. And when we do that, we're going to get 1 barium chloride, which is what to be expected. There's 1 barium chloride to a certain number of moles of water. When I take 0.0411 divided by 0.0205, we get pretty much 2. So now I know the value of X is 2. For every barium chloride compound, 2 water molecules are attached to the structure. Now, unlike empirical formulas, when we do a hydrate compound, we should always get a whole number because we can't have a fraction of a water molecule. So we should have whole numbers whenever we do a hydrated compound to figure out the value of X. So again, step 1, we find the mass of the water by subtracting the before and after mass. Step 2, we convert the mass of the water and the mass of the salt. We convert that to the moles. And step 3, we divide the moles of the water by the moles of the salt, and that will give us the value of X, and that's how we do a hydrate problem. Again, a 3-step process, fairly simple when you have just enough practice that it becomes just robotic. Okay? And that is how we do hydrate problems, and now you have homework problems to go ahead and practice and get comfortable with before we take the test in about a week. Again, thanks for listening.